Okay, so this is something I started to put together as a starting point for solving ham RFI issues. There's some of this in there that their presentation was certainly better than mine, but I had to start somewhere. And I'd originally expected to have 20 minutes to do this, but I got 15, so we'll see how it goes. One of the things I always try to tell people is when it comes to RF, it's bidirectional. If it gets out, it also gets in. So you gotta worry about that it's bidirectional. And one of my favorite slides is this slide. It's, for one, it shows you how you can quickly turn a piece of coax into a usable antenna. But it's also, part of it is showing you the importance of controlling return current. What people don't realize is that the power that you're pushing down that wire, the center conductor, goes through the air, hits the shield, and comes back on the shield. So there's actually current flow through the air. And it's when you don't control that current flow, you have radiation. And a quarter wave pattern, you guys know what that looks like. Ohm's law, Bacher, I mentioned that earlier. When it comes to RF, not only do you care about resistance, you also care about inductance. Is it near field or far field? Something that hams don't normally worry about is that when you're within, and depending upon who you talk to, it changes. Anywhere from 3 wavelengths to 1 wavelength is near field. The importance of that is you can have a signal that's near field that's, when you're against it, you're 50 dB over S9, you move out 1 wavelength and it goes away completely. Far field, if you move a wavelength out, you can calculate what the level is. Near field, you can't. If you're within the near field, you have capacitive coupling, inductive coupling, and so on. Where if you're in the far field, you're basically back to working with antennas. What are the FCC requirements? One of the things that in the FCC rules is that operation of an intentional, unintentional, or incidental radiator, which is all your, well, that includes everything. If it's subjected to conditions that has harmful interference being given to it, the device must accept that interference. Now, it must accept the interference from an authorized radio. The catch with this is that the FCC doesn't actually specify how you test it, how you confirm it, or anything else. It's just left up in the air. Europe actually defines it. The emission levels for the FCC is shown here. Here's what it looks like. The red is Class A, the B is Class B, and the reason why there's 2 levels is one's the levels if you test 3 meters away, and one's if you test 10 meters away. The Class B level at 40 dB microvolts is 20 dB over S9. So these levels really aren't all that great. And this slide shows you where you can see the formula where I said it was 20 dB over S9. Modern computers with having USB-C ports have USB-Cs that are capable of 20 gigabyte speeds, and if they're the Thunderbolt capable, they're capable of over 80 gigabytes. And I understand that Thunderbolt 5 is even faster than 80. So anybody who's designing a motherboard for a modern computer that has USB-C on it, they're going to do a really good job of designing an RF quiet board, because their USB-C port's not going to work if they don't. They also probably have spread spectrum clocks in the system, and they cannot be turned off. If you go back 30 years ago, you could buy a motherboard, had spread spectrum on it, but it was your option whether you turned it on or off. Nowadays, it's turned on, you can't touch it. So here's a modern computer. I had a FCC lab, a company that does FCC testing, send me plots from a recent computer test. So this is what a typical computer looks like nowadays. And if I can turn this on. So down here, this down in here is probably due to the switching power supplies on the motherboard. The one motherboard I just bought has 27 switching power supplies on the computer board. Here's a plot of the frequencies from 1 gigahertz up. Here is what the conducted emissions report is from a TDK medical power supply. They had it posted on the web, so I grabbed it. The Samulex Power was kind enough to send me plots from one of their power supplies. This is what the conducted line looks like from the line side of the power supply. And that's the chart of the levels. This is what the neutral side looked like. And the plot for that. And here's their radiated emissions. And they ran to the Class B at 3 meters. And as you can see, that's almost 10 dB of isolation, of difference there. So their levels are pretty recent. Here's the same thing in plot form. You can see their margins, 7 dB, 8 dB, 13 dB, 11 dB. So they got reasonable margin. For production unit, I like to see 6 dB. Prototypes, I like to see 6 dB of margin. Production, I like to see 3 dB margin. So this power supply would meet my, my normal requirements. Back when I used to do actually do certifications. Now, one of the things we talked about isobars earlier. Here's a picture of the inside of a trip-lite isobar, and you'll notice that it's got capacitors, it's got inductors. It's not just surge suppression; it's a RFI filtering. It's anywhere from 40 to 80 dB of RF suppression, which is one of the other reasons I like it. Not only do they have lightning suppression, they've got RF suppression in it. Also, routing of power cables and signal cables and coax is important. You want to keep power cables and you want to keep your DC cables away from your coax. Your coax away, you want to keep all three separate. It's also important how you route them. I like to, on my radio desk, I got like 2.5 feet of separation between power and coax. But also, the one thing I wanted to point out, this picture of a power supply, these things over here are EM shields, they're not magnetic shields. Now, the reason why I cut this power supply apart was it was being used at a location that had 3 Kiwi SDRs, and they were having serious issues with noise. It was this power supply. So I cut it open just to see what it looked like inside. But one of the things you have to watch with these switching power supplies is right there is the switching coils. And in this particular case, there's a ground wire going across here. That ground wire is within the magnetic field of those coils. So those coils are driving switching noise onto the ground out both ends of the power supply. So that's why it was so noisy. So the point of that is when you're mounting if you're using a switching power supply, don't route wires on top of it. Don't like coil them up and toss them on top of the power supply. If you coil up some wires and throw it on top of that inductor, it's going to inject a significant amount of switching noise into those wires. So when you're using switching power supplies, you got to be careful about wire routing around them. I use switching power supplies. I don't have problems with them, but I'm very, very careful about where I put my wires. The wire's external to it. There's no wires against it. The wires are always away from it. Okay, so for Europe has requirements for RF, not only the emissions like the FCC does, they also have RF susceptibility. You have to actually take products into anechoic chambers and test them to make sure they don't respond to RF fields. You have to test them for ESD. You have to test them for lightning, surge, and magnetics. So anything that's truly being sold in Europe is probably pretty good RF-wise. Medical equipment, there were some concerns about medical equipment. The FDA actually requires compliance with European standards, which requires a susceptibility test. One of the things I try to convince people when I'm reviewing boards and things like that is people like to put what they call motes in circuit boards. Well, the problem with that is when you do that, you end up creating an antenna. Here is this is how you can make an RF probe. If you want to do RF diagnostics, you just break the ground on this loop and you got yourself basically an antenna. And this is a probe example. Right there's no ground. All this is shielded, it's all grounded, and the center conductor is actually grounded right about there. But right here, there's no ground. It's a basic antenna. And that's how you can use to isolate noise on a circuit board. This particular one is from RF Explorer. It used to be available for $110 plus shipping. I got a suspicion they may not make it anymore. Another way you can make a probe is just take a piece of coax, RG58, and you can see the pictures here. You just cut it off, strip it back, bend it over, put some shrink tubing on it, and you got yourself what's called a bazooka antenna. I recently had a case to use one of these. We had, at the site where they had the Kiwi SDRs, all of our search antennas, all of our diagnostic antennas had so much field to it, we couldn't isolate the source. So we switched to this, and we were able to get it down to a specific device. Here's another probe you can make. Let's see. My reason for watching for breaks and grounding is if you have a box like this, the two boxes that are connected together with a fully shielded cable, for all intents and purposes, you have one enclosure. So you always want to make sure your shields are 100% 360. It's no cutting corners. There's, for low-cost things for finding sources, HTs, nano SDR, you can use SDRs. Dipoles, look for the nulls and not peaks. Ken Britton is usually out there in the flea market. He sells circuit board antennas for cheap, and he's typically in spot 8121. Frequencies to worry about for local interference, you got frequency references, 10 megahertz, Ethernet's 50 megahertz increments, USB's 12 megahertz increments, and VGA's got a ton of them. And most computers have got spread spectrum and have clocks in the gigabit range. Don't use cheap cables. Cheap cables are not made well. Use only C2G, trip-lite, HP, Dell cables. The cheap cables you're going to be forever sorry. Don't use cheap coax cable. Inside the shack, I basically use like LMR 240, LMR 400, sometimes RG220, RG 400, RG 142. Outside, you can use the cheap stuff. Inside, don't. Don't buy cheap devices or computers. If you're buying something on Amazon, a lot of that stuff doesn't have safety certifications. It doesn't have valid FCC tests. That's why they're cheap. Today, if you wanted to get an FCC test done, they're about $8,000 to $9,000, something in that range. If it's got transmitters in it, it could go even more. The last product I had quoted before I retired was $900,000 to get it certified worldwide. So if you're buying something for a few dollars on eBay or on Amazon, they haven't been tested. You're buying an unknown, and it's most likely an RF source. I call ground loops, I'd call it antique misnomer, and this slide goes in. I'm basically out of time here, so I'm going to bounce to the last slide. If you take a picture of this, you can download the presentation. And if by some chance it doesn't work, just send me an email at my call sign at arl.net, and I will get it to you.